Okay, so as I said, so far, we've only looked at V is a constant. Example would be a battery. Now we are looking at alternating source. So this plus we'll be looking at V is a function of time, and that is, let's say, Vm sine omega t plus P. So this is alternating source because the voltage is not steady, constant, but it varies as a function of time. Here Vm is the amplitude. Omega is the frequency. T is clearly the time. And phi is the phase. So if phi is greater than 0, it's called a leading signal, and phi is less than 0 is lagging. When I say leading and lagging, that is with respect to a signal which doesn't have the phase. So if phi was 0 on another signal, then how would you compare this signal with that one? And that will be clear in just a bit. So let's draw this voltage as a function of time. Okay, so I'm drawing first the voltage V equals Vm sine omega t. And the reason why this is Vm sine omega t is because if you put time t equal to 0, you see that V is also equal to 0. The magnitude or the amplitude is this Vm. And if you want to now look at a signal, which is the one I wrote down earlier, let's draw it in this fashion. So this is my V equals Vm sine omega t plus phi. In particular, if I put phi equals 0, then I see that this is my y-axis. It will be Vm sine of phi, right? If you put t0, then this signal you can see at time t equals 0 is leading the signal. So phi is positive, which means that the signal is leading. And so you can take a snapshot at any instant of time and then compare. It's easiest to take a snapshot at time t equals 0. And then the final thing I want to talk about is the frequency. The frequency is omega, but if you want to write it in terms of omega is, you can see from the expression that the units of omega is 1 divided by second or second inverse, because when you multiply that with time, you should get a non-dimensional quantity like the phase. Another way people write this is in terms of f. It's just taking the, just dividing omega by 2 pi, and then that frequency f is usually is the one which people sometimes write as frequency instead of they just divide by 2 pi. There are two ways of doing that, right? So this is how an alternating voltage is written. Now what we'll do is we'll write it in terms of, you can also write it in terms of complex numbers. Yes, so complex numbers. Okay, complex numbers have an example of complex number would be 2 plus let's say 3j. Okay, where j is equal to square root of -1. And so this represents basically not a scalar, but a vector, because whatever is over here is the real part, and whatever here is the complex part. One way people like to show this on a plot is that this is the x-axis, this is what is on the y-axis. So 2 plus 3j on the xy axis would be x equals 2 and y equals 3. Bit down. So 2, 1, 2, 3. So x equals 2. This is 2 plus 3j. Okay, so we can take this idea of complex numbers to alternating current because it has a phase and it has a magnitude. So we will use this notation. E is the exponential j omega t plus phi is basically one way of writing complex numbers. This is also cosine omega t plus phi plus j sine omega t plus phi. Okay, so I will not get into the details of how this comes like this, but this is I think it's called Euler's banking on the name. But if you search for exponential representation of complex numbers, you should see how this is derived, how this is equal to cosine plus sine. So what we can do is we can represent V as Vm e raised to j omega t plus p, which can be written as Vm cosine omega t plus phi plus j sine omega t plus phi. Okay. One way people write this is Vm with phi, which just means that this has a phase of p. Now, this is also called as the polar form, and this is also known as the rectangular form, okay, which is similar to what I written on earlier. When it's in written rectangular form, you can show it on the xy axis like I've shown. You could also do the polar coordinates in this form, but let's skip that. So when you look at alternating current, we can always write it as a Vx plus Vy, with Vy is j coordinates. And if you want to find the magnitude, you just take the square root of sum of squares. And if you want to find the phase, it's tan inverse of Vy divided by Vx. Okay. So the reason why I wrote down all this is because we will actually use this particular form to write the voltage which is varying, and that will actually give us, will make it quite easy to analyze circuits involving inductors, resistors, and capacitors. So let's see how to do that. So now we'll take this idea of using complex numbers to the next part and show you how it just makes our life very easy when it comes to simplifying complex circuits. Let's start with the resistor, then do the inductor, and then the capacitor. Okay, so what we'll do is, the big idea here is we write the voltage divided by the current as Z, where Z is known as the impedance. And this can be complex number. A complex number has that real part and the complex part, like 2 plus 3j I wrote down earlier. So what we'll do is we'll reduce the resistor, capacitor, inductor to this form. We'll find the equivalent Z for each of them. And once we find equivalent Z, this expression actually looks very similar to V divided by I equals R, like what we do for a resistor. And so everything will boil down to something which looks like a resistor. And once we have written down expressions similar to a resistor, we can then start using some of the tricks we've used for parallel, series circuit, and so on. So that will be clear when I do this. Let's just first derive the expressions for Z for various elements we've talked about so far. Let's start with the resistor. For a resistor, we know that V equals Ri. So if you want to put it in this form, we can write this as ZR times R, where ZR, or the impedance for a resistor, is simply R. The impedance of a resistor, which is similar to a resistance, is simply constant, and it is R. Okay, next, let's do this for an inductor. We know that the expression for an inductor is L di dt. Okay. And we are trying to reduce this to something which looks like V equals ZL times I, where ZL is the impedance of an inductor. Okay, so what we'll do is, the easiest way to do this is, let's assume that the current is sinusoid. So I am e raised to j omega t plus pi. Now you could also do this with voltage, just it's much simpler to do it with current, because then I can differentiate. If I do it with voltage, then I'll have to integrate it, but you'll get the same result. So let's put this in the first expression for V equal, that is V equals L di dt. So we have di dt. Here is Im is a constant. The derivative of exponential is basically the exponential itself, and then you take the derivative of this part, right? So j omega t, so d dt of j omega t plus p. So when we, this is basically applying the chain rule. So the derivative of j omega t plus phi is just going to be j omega, because phi is a constant, so that eliminates, becomes 0. So with this expression, now we can sub that in this formula. So we have V equals L di dt, which I wrote down as Im exponential j omega t plus phi times j omega. I think I'm missing something. No, that's right, j omega. Okay, but this thing is the same as I, because remember we started off assuming I is Im e raised to j omega t plus phi. So this expression boils down to j omega L, that is, I'm taking this term and this term together, times I. And so we can see that this is ZL times I, which means that the impedance of an inductor is j omega L. In other words, the impedance, which is similar to a resistance, is proportional to the frequency. So bigger the frequency, the larger the frequency, the larger is the impedance of an inductor. This is for a resistor. Okay, so what does this imply for a circuit with constant source? So what if omega is 0? In other words, it's a DC source. That is, if the inductor is connected to a constant voltage, which is omega equals 0, then we see that Z equals ZL equals 0. In other words, what's saying is that the resistance is 0, which essentially means that it is a short circuit. A short circuit happens when the resistance is 0 resistance. So what we can do is we can replace this circuit with a wire. This is short circuit. Zero resistance. Now, zero resistance is bad because what happens is now you're connecting the positive to the negative, and it will probably lead to unpleasant things. It could even blow up the power supply. So you don't want to connect the positive to the negative without connecting to some load or some resistance. Okay, so short circuits. Never connect an inductor directly to a voltage source because it lead to a short. Okay, now let's look at what happens to a capacitor. For a capacitor, we wrote down Q equals CV. Okay, and we're trying to now compute or try to boil this down to ZC times I, where ZC is the impedance of a capacitor. Okay, so what we'll do is, in order to get this, let's differentiate this expression. So we have dq dt is C dv dt. Okay, C is a constant, so constant stays, and we get the derivative of V. So which means that I equals C dv dt. So in order to make this into ZC, what we'll do is we'll start assuming V equals Vm exponential j omega t plus phi dv dt. Like the previous example would be exponential j omega t plus phi times j omega. And now if we sub this in this expression, we have I equals C times Vm exponential j omega t plus phi times j omega. But we did assume this to be our voltage, so we can then put all this together as j omega c v. Okay, just move this over. Okay, but we want to write it as V divided by I, or V equals ZCR. So what I'm going to do is I'm going to multiply both. Let me divide both sides by j omega c. So I'll have I divided by j omega c equals V. Okay, let me move on to the next page. So I wrote down V equals 1 divided by j omega c times I. And so I don't like the j in the denominator. So what I can do is I can multiply the numerator and denominator with j. So I would have j square I divided by omega c. But j square, remember the j is square root of -1, which means that j square is -1. And so we have V equals minus j divided by omega c times I. And this is ZCI, which in turn gives us the value for the impedance of a capacitor. It's minus j divided by omega c. Okay, now that we have this, we can now look at the effect of connecting a capacitor to a DC source. For a DC source, omega equals 0, which means that ZC equal to infinity, putting that equal to 0, which means that if you take a voltage source and connect it to a capacitor, then this will lead to an infinite resistance. Infinite resistance means it's an open circuit, no current will flow. So this is an open circuit. Current is 0. So if you want a very high resistance to flow, you want in a DC circuit, you want to put a capacitor. If you want a short, you need to put an inductor. Okay, so this is the fundamentals of reducing capacitor inductor to an impedance. Now let's see how to use this thing we've done in order to analyze a complex circuit involving resistors and inductors and capacitors. I'll just do a simple example, but you will hopefully get the idea, and then you'll be able to do more complicated things. So the example is this. Okay, consider this circuit. Okay, this is the alternating source, and let's assume that there's current I flowing here, and then I'm just going to say that IL and IR are the currents in those two branches, and this is our first circuit which involves two of these elements, which are not just resistors but an inductor. So if something like this shows up, you will typically be told that V is a AC source. Okay, the question is compute I, IL, IR. Okay, the currents in the individual branches. Okay, now one of the advantages of what we've done so far is that we have reduced everything in terms of a equivalent resistor. The impedance is like a resistance. And so we can use the same formulas we looked earlier in order to analyze this. What I mean by that is we can actually write this as ZR and this as ZL, where ZR is R, ZL equals J omega I and okay, now okay, let's go on to compute these values. In order to compute I, what we'll do is we'll try to combine this impedance with this impedance. And the way we do it is we think of what circuit does this look like, which has only resistors. This looks like a circuit involving two resistors in parallel. So we can use the same formula for resistors in parallel because this has an equivalent expression, V equals Z times I. So ZR and ZL are in parallel. And so we can write the equivalent impedance as ZR, ZL, ZR plus ZL, where ZR and ZL I've turned down there. This is because ZR and ZL are in parallel. Okay, so once we have that, we can compute I. I is nothing but V divided by Z, right? Because we've reduced the circuit to something like this. This is I. And so this is going to be V divided by VR CL, VR plus CL. And then the last step is to actually put in the values for ZR and ZL, which I've written down here. Let me just write it down. So ZR is R, ZL is J omega L, J R, J omega L R. That's the final expression. Okay, now let's compute the currents to the two branches. For that, let me just copy this. Okay, now so far I've computed the current I. That's known. Now what I'm going to do is I could technically write the KVL and compute what IL and IR is, but I can instead use the current divider rule. Remember the current divider rule, which says if you have two resistances, R1 and R2, and then current I is flowing, then I1 is R2 divided by R1 plus R2 times I, and then I2 is R1 plus R2 times I. Okay, so this is the current divider formula, which I devised last time. I'm just going to use that. So I is known, so I can then write this as I R equals ZL, ZR plus ZL times I ZL, but I is V divided by Z, and Z was ZR, ZL, ZR plus ZL. So the ZL cancels with this ZL, this ZR plus ZL cancels with this, and we're left with IR equals V divided by ZR, which is V divided by R. Okay. Similarly, I can write down IL as ZR divided by ZR plus ZL times I will be ZR divided by ZR plus ZL times V divided by ZR ZL ZR plus ZL. So this cancels off with this cancels off with this, and then I'm left with IL equals V divided by ZL, which is V divided by J omega L. This is IL. Okay, so this is how you can take something which is very complicated, capacitors, resistors, inductors, and simplify them to something which looks like a resistor or an impedance in this case, and then use whatever we've learned so far to simplify the expression and then solve it. Okay, and so for the homework, you'll see problems involving capacitors, resistors, and inductors, but it's not hard now that you know how to convert them to an impedance.